So now let us do a timing analysis on this and see what happens. Okay. So what I'll do is, maybe I will copy another diagram and we'll do it on that. So for simplicity now, I am going to assume the following. T sum equal to 1, T carry also equal to 1. So I showed you a circuit also where this can be achieved. Equal delay for carry and sum. Okay. So now we are going to do, and of course, T and also equal to 1. So now let's do a static timing analysis on this block and propagate these signals to the half adders, and assume everything is a full adder now. Okay. So the arrival time at the output of every AND gate, at least the first AND gate, is what? Actually every AND gate. Yeah, because all x's and y's arrive at time 0, right? This is what is known, x0 to 3, y0 to 3, arrival time. Equal to 0. Therefore, everything will arrive at unit time here. Correct? What about the, of course, these AND gates also are the same. Okay. So now the first half adder, what is the arrival time for carry out? This guy. It's going to be 1 plus 1. This will be 2, 2. Right? Full adder, next full adder. 3 and 3. 4, 4. 5, 5. Right? Next stage. What is this? 4, 5, 6, 7. Last stage. Yeah? You take max arrival time, right, of both inputs 1 and 5, 5 plus 1 unit, 6, 6, 7, 7. Now of course the 6, 6 is the same. For this full adder, this one A or B is arriving at 6, the carry is also arriving at 6. So max is 6 plus 1 unit, 7, right? This will be again 8, 8. Oh no, sorry. This will also be what? 7. So this will be 8, 8. And this will be 9, 8 plus 1. Correct? So this is 6, 6 plus 1, 7, right? And this is 8. Yeah. Okay. Now, what is the critical path of this block? So you got to pick the output. What are your outputs? For this multiplier block, right? My multiplier block 4 cross 4 mult is basically A 0 to 3, B 0 to 3 and output Z 0 to 7. Pick the output which has the maximum arrival time. Which one is that? Z9, I mean Z6 or Z7. So I will track this in this. Now, which input has arrived last there? This guy. Now which input has arrived last? Both, right? Effectively, what this is saying is there are multiple critical paths, all with the same delay. So it is impossible to sort of optimize this because everything is equally critical. Now which one, if you want to optimize one critical path, there should be another path which you can sacrifice delay on. Then you can optimize. But now there are multiple paths, right? So for example, you can go like this, right? Or you could go like this, or any other path you take, right, to arrive at 7, everything is similar time. So there's nothing that you can do in order to optimize this path. So you also notice what is happening is, if you take every single stage here, right, if you take a single stage as, I run out of colors, okay, if you take this guy, it's basically like a ripple adder, right? I'm basically just rippling my carry through that stage. Each row I'm rippling my carry through that stage, correct? So that is really not helping me. So now we will come to what he pointed out, that it is really not necessary for you to ripple the carry along the same row. I need to add it, right? When I do x1, y0, I have to add it and get a carry, and the carry needs to be propagated to the addition of and contribute to z2. But it need not happen this way. It can also happen this way. You add x2, y0, x1, y1, and when you're adding with x0, y2, you basically add that carry. You follow me? I need to add 3 numbers, x2, y0, x1, y1, x0, y2, plus a carry that's coming from the previous state. I need to add 4 numbers. That can be done in many ways. I'm saying you do x2, y0, x1, y1 first. Then you get the sum. Then you add that carry. The advantage is, while x2, y0, x1, y0 has generated a sum, that previous carry would have also got generated. And the hope is these signals will arrive together. Right? So in some sense, instead of adding the carry immediately, you are saving the carry and adding it later. Right? Therefore, the next architecture of multiplier, we are going to basically call a okay. By the way, if I were to, assume x is m bits and y is n bits, then what is the expression for the critical path delay of my array multiplier? Yeah, 1 second before I do that, let me check if my notation is correct. This m and n. So that's what I don't remember. Oh, sorry, x is n bits, y is m bits. I'm sorry. Okay, so that we don't get confused with the expressions later. Okay, this is m bits, n bits. I'm sorry, n bits, and this is m bits. Okay, now let's not assume t sum, t carry and all that, equal to 1. We will write it in terms of that delay. Okay, so what is the delay? So what you do is you just track this blue line here, right? How many carry paths does it have to go through? No, remember, this blue line ultimately has to come all the way till here. how many carry paths does it have to go through? No. So if x is n bits, y is m bits. So let us write that expression. T array mult. Of course, the first delay is the time to generate the partial products. 1 unit of time is needed for that, which is T and. Now it has to go through some number of sums and some number of carries. How many of them? N plus m minus 2 T carry plus how many T sums? How many T sums? Basically, this is one T sum, another T sum, another T sum, right? That's how many T sums? Huh? Yeah, that is actually a carry. Okay, what I meant was this is a T sum. So how many T sums? No, we'll verify this answer. We know the arrival time has to be 9, right? So we'll plug in these values 1, 1, 1 and see what we get. And then we'll see where we went wrong. One, two, and I would say for 4 bits, it's 3 T sums. Right? You got to go through this guy, and then this guy. Right? So, is this right? First you substitute and see, then we'll see. For n equal to 4, m equal to 4, T's and T carry T sum are all 1. How many T carries? N plus M minus 2. So 1, 2, 3, 4 is what I am getting here. Plus makes sense. M minus 2. Correct. Okay. M plus N minus 2. Okay. Now substitute and see, do we get 9? We do. Right? Okay. This seems to make sense. So let us see if the answer matches from what's given in the textbook, just in case we have made a mistake. M minus 1, yeah, this is what I thought. M minus 3 T carry plus M minus 1 T sum and T and. Why did you say m minus 2? That depends on the path, no? So I understand that, yeah, it could be, maybe it could be this also, right? One path might be this. I think the other path is t and plus n plus, let me write it differently, m minus 2 plus n minus 1 t carry plus m minus 1 t sum. I think, why? No. Yeah. In the, okay, I agree in the sense that this guy, blue line, has to go through this and then come here. Then it has to go here. Yeah, you're right. Yeah, you're right. Right? And then again, it comes here, arrival time here, and then it has to go here. Correct? Yeah, this makes sense. Yes, I agree with you. Okay. So basically what we are saying is, there are how many t sums? 1, 2 and 3, which is m minus 1 t sums, right? And the remaining are basically your carries. So I have x being an n bit number, I need to go through n minus 1 t carries and another m minus 2 t carries for the y direction. Clear? So it's just a question of counting how many carries and sums you have to go along the critical path. So therefore, I would think this is a more appropriate answer. Yeah. Yeah. Correct. So in some sense, we have basically, not represented reality perfectly here in this arrival time picture. Right? So you're right. Where there are more t sums, that's what we have to do. And in fact, if you take, so I'd say you go back and work this out for, if this were 2, t sum were 2 units and t carry were 1 unit, then you will find that this guy is actually the signal with most delay, because you have to wait for that sum to come out. Then you go only along the sums, propagate it, and then you can find, I think this will turn out to be the right answer. Basically, like you said, m minus 1 t sums as opposed to m minus 2 t sums is the exact answer. Okay? So let me just maybe write that out again. T array multiplier is equal to t and, right, plus m plus n minus 3 into t carry plus m minus 1 t sum. Okay.